Hi, and welcome to Module 3. In this module, we will explore HPE's most common architectural patterns in detail. We will refresh our recollection of our most fundamental pattern, the web service based on the Addison module. We will explore additional architectural patterns covering the major functions performed by our applications. And as we study each architectural pattern, we will revisit our example channels domain from Module 1 and explore each of the patterns found within that example in the context of the formal patterns presented here. Let's get started. Architectural patterns generally come in two types. Logical application architectural patterns focus on the requirements at the code, process, standards, and supportability levels around each type of pattern in order to perform a specific function. For example, offloading processing of CPU-intensive tasks, handling large queries, or possibly using special messaging algorithms or standard transmission protocols. Our enterprise architecture team has identified these and can provide them on request. Physical application patterns, on the other hand, refer to the standardized black box system functional components required to perform a specific function. The ones that we will examine here will be the physical architectural patterns. So first we'll start with a refresher on our most fundamental standard component, the basic web service based on Addison. The second group of application patterns we will look at are generally referred to as client applications. Here we will find our typical three-tiered web application. We also find mobile app to web service or to API, or a device to web service or API in this group. But we will exclude those from scope because those are really a subset of our first pattern, the basic web service, with an added client or device that can be considered completely independent of the API. For example, if we have a mobile application, the complete application usually resides on your telephone and communicates back to the corporate network via a web service interface. But the two are completely independent. The third group of architectural patterns that we will examine can be referred to as application-to-application interfaces, or A-to-A. Here typically a client is not involved. These patterns refer to use cases where systems are exchanging data between each other. We will begin with the ground-to-ground pattern, which can come in multiple flavors depending on the structure of the data, but which typically refers to two applications residing within the corporate network. As we will see examples of the ground-to-cloud pattern as well, most commonly found with SaaS solutions sending data into the corporate network. An example would be Salesforce, sending to HPE. We can argue that a B2B pattern is a special case of this pattern, but we will treat them separately. The cloud-to-cloud pattern will be excluded from the discussion for now. This pattern refers to two cloud-based applications communicating with each other, for example, such as Salesforce communicating with Sales Dynamics. And in this case, we will employ native plugins, usually available on the cloud application's own marketplace for most common combinations. This solution will require licensing and will be used only in special cases. Finally, the fourth group of architectural patterns that we will examine will be the B2B or business-to-business patterns, often generally referred to as EDI, but there are other variations. Here, a customer system sends transactions data into the corporate network via a standardized interface using industry-standard protocols or files. Here we will find the partner direct sync pattern, for example, where a partner's call center system is linked directly through a gateway into HPE's support center system in order to log support calls in real time. An example of this is how H3C in China logs calls for response by HPE. We can also have partners sending files directly using an agreed upon format between the two parties in cases where an industry standard format does not exist. For example, bulk service registrations are handled in this fashion. The third set of patterns will be built upon standard communication protocols, such as RosettaNet and AS2. Here, an industry standard is being used as prescribed, with data transmitted between a pair of formal gateways possessing all the features and characteristics that typically define a business-to-business gateway, or service bureau, for example, like an EDI value-added network. As we explore the various architectural patterns, we will use a standard template for ease of illustration. We have subdivided the template into columns representing the various layers of the solution, each listing its corresponding technologies at the bottom of the column. The first and last columns represent the core runtime platform with its accompanying data services. The platform is the light gray box in the background. Note that the vast majority of our applications and services will run in this layer. Starting with column 2, from left to right, we see the UX UI tier and the application or middle tier. Apps and services running in these tiers will be represented by symbols called out in the legend found at the bottom of the standard template page. Throughout the patterns, you will find brick-colored boxes with a dark blue border. These represent containerized services based upon the Addison module. Bright blue boxes with a dark blue border represent UX UI components based on HPE's own PageMill framework, which is in turn based on React.js. Note that the PageMill container also contains an Addison server for ease of deployment. When used this way, there is no need to set up a separate web server such as an Apache to run your PageMill app. If you don't see it in a diagram, assume it's there. Small boxes in olive gray represent various common services available for use by all applications and considered to be part of the platform. These may also be based on Addison. As we move to the right, we encounter the integration fabric, the central messaging function supported by Kafka and NiFi, and the data lake, where all data will flow either in real time or near real time, including monitoring and instrumentation feeds. All those services are supported at the very far right by our data cloud, which is one of the core pieces of the platform. We will use this standard pattern in this standard template as the basis for depicting each of our other architectural patterns as we move forward. Finally, before we dive into the individual patterns, let's refresh what we learned about Addison in Module 2 of this course, since it is so central to and common throughout the patterns. Each time we encounter Addison services in the diagrams, we should remember the various things that are automatically happening whenever we deploy Addison. These are illustrated here and are called out in the application tier technology list at the bottom of each page. But for purposes of diagrammatic simplicity, we have omitted the illustration of these various repetitive flows each time we illustrate an Addison component. However, it's important to remember that these things are there, providing services to the developer and saving a great deal of additional work. Now, let's dive in. Our first architectural pattern is the basic web service based on Addison. As we saw in Module 2, Addison consists of a single server JavaScript file and the bare essential configuration files to enable the server. The module only needs that core package to run as a fully working application. Addison comes fully pre-configured by adding routes, logic in the form of handlers, and any additional packages necessary to enable that logic. Addison can easily provide a fully working, self-contained web service that can run within a Node.js container with very little additional work. Remember too that Addison is fully instrumented and provides a variety of embedded services on go live. Let's take a look at an example of Addison as a web service. In this example, we have added one package, the MySQL npm package, and two new logic modules, TestTable.js, which provides an AJAX interface for the UI, and db_mysql_API cat, which contains DB connection strings, connection pooling functions, and SQL queries to allow us to communicate with a backend MariaDB database, which is MySQL compatible, running in HPE's Database as a Service cloud. These simple additions create a fully secured, instrumented middle-tier application that can serve direct web service requests using REST JSON calls. We can see the interface at the lower left, titled WS. It also has the native ability to serve requests via HTTPS, which allows the use of a browser running a CORS-enabled UI independent of this middle tier, using AJAX to issue its database requests, or embedded within the application, as we will see in the static web server and three-tier web app examples coming shortly. Architectural pattern 2 represents a static web server application, a common pattern that can occur both as standalone application or embedded within other apps, and which we typically use to present marketing, training, or informational materials to our stakeholders. Also note other components in the drawing which represent the runtime environment, platform services, and data and analytics functions called out in the definition of the modern application. In this example, we have taken the previous web service example and leveraged the inert plugin within Happy to now create an embedded UI for our application. We can see it in the large purple box near the lower right. Inert provides Happy, and thus Addison, with directory and file system manipulation functionality, allowing us to create a self-contained web server that is capable of serving up static and dynamic web pages. Here the user can access our HTML pages directly from the Addison server via secure HTTP at the left of the diagram. The pages can then in turn communicate with the server via its native REST interface, titled WS on the lower left, or via HTTP calls using AJAX to interact with the database. The same functions available to a browser via REST-JSON are also available to other applications and systems that can use the API as a web service to call our app directly. We can treat a compiled or minified Grommet application in exactly the same fashion, using inert and providing an embedded route to call its HTML file and thus invoke the application via the HTTPS interface. This is typically the way we launch containerized Grommet apps today. Next, combining patterns 1 and 2, we can now see how easy it is to create a complete and fully containerized 3-tiered web application using the Addison module. When we add middle-tier services and a backend database, we now have what we know as our typical 3-tier dynamic web application, where we can actually perform operations on data in an interactive way with a user or partner. Here we illustrate a DB which contains local master, reference, and user data to drive the application. In this example, from our channels domain, Pattern 3 is illustrated using multiple containerized Addison modules, each performing one of the many functions within this composite application. One of the principles of Node.js is that each package should perform only one function and do that function exceedingly well. This allows each individual function to be scaled independently of the others when called for, greatly optimizing the infrastructure footprint. Here in our channels example, our modules are optimized for entitlement checks, part orders, labor claims management, and BOM or bill of materials checks. Remember from our Addison diagram in patterns 1 and 2 that each module is itself a collection of smaller modules, each performing a highly optimized code level function, and that the Addison collection as a whole is fully instrumented and providing services automatically upon deployment. In pattern 4, we deal with 3 flavors of app-to-app or A-to-A integration. In the first case, at the top, we have 2 commercial off-the-shelf applications, one of them being SAP ERP, which plays a prominent role in the HPE landscape. These applications typically have incompatible data models and thus require a translation or wrapper in order to enable communication. In this case, we rely on 2 Addison modules acting as web service wrappers in front of the applications, translating each proprietary data model into a common EDA or enterprise data architecture model, allowing the data to be reused universally within the HPE landscape. The data flows through a message infrastructure, the integration fabric, fronted by Addison modules which regulate the flow of data to and from Kafka, and to the data lake, whose ingestion and downstream consumption interfaces are also composed of Addison modules. The second case illustrates a custom application whose data model is already EDA compliant. In this case, the translation wrapper is not required, and the data flows directly to the messaging interface. In a third case where a web app or other application might need a real-time response from the back end, the dotted line illustrates a direct request-reply connection through a published API on the service infrastructure platform, or the enterprise platform. The published API takes care of the wrapper or translation functions to ensure a consistent data model. In example 4, we have added the direct real-time app-to-app integration to our channels example, adding connections via REST services and API wrappers to the back-end ERP system, for example SAP, allows the web application to directly interact with the back-end functions. In this example, a channel partner directly accesses functionalities like order management, installed base, entitlements, and partner labor claims. Architectural pattern 5 illustrates a special case of the app-to-app integration, where the ERP or other back-end system specifically publishes master and reference data via a published API for consumption by other downstream systems. Here, the data being used by our example channel application for reference purposes is specifically the BOM, or bill of materials, which it leverages while processing other partner transactions, such as orders and service entitlements. Pattern 6 illustrates a cloud-to-ground implementation of the Salesforce interface, where the partner is actually performing most of his work via the Salesforce UI, and in this case, files a labor claim which leverages all of the same services and back-end applications previously seen in the three-tiered and B2B examples. Note that we added a second example, a location service, also using a cloud-to-ground connection, in order to send an address and actually generate map coordinates, allowing the partner to find the location of the customer where service is required. Pattern 7 illustrates a B2B or business-to-business service pattern in slightly greater detail, showing the message translation and wrapper packages within the service. Here we illustrate two possible cases from our channel example. In both cases, the partner is sending a file using an agreed-upon format directly to the HPE proxy service. In the first case, the file might contain bulk service registrations or bulk service orders for special products that cannot be accommodated via standard B2B. The file would flow asynchronously through the messaging services, guaranteeing delivery, and then to the downstream ERP system or other backend for processing, following the dotted lines. In the second case, the same pattern can also be used to integrate a partner's external system, such as a call center system passing cases to HPE for resolution, via XML messages that may require a real-time response. Here the connection is directly between the service and the backend ERP or call center system, the dotted line in the drawing. Please also realize that the box labeled Function API Wrapper might live independently as a published API within the service layer. In example 7, we use the same services that we reviewed in our three-tiered web application example, but have substituted the UI with a web proxy that interacts with the same backend services. It allows the partner to send a file, which can be checked for accuracy using reference data services such as the BOM service, then processed via the ERP system as an order, registration, claim, or request for entitlement. Though admittedly simplified, this example clearly displays the high degree of reusability of a pattern-based architecture. Finally, Pattern 8 illustrates a formal B2B deployment using a standards-based gateway product or provider, in this case Seaburger, which is used by the partner to send bulk orders for standard products, such as small servers, in larger quantities. Here the order goes directly into the messaging interface in the form of a RosettaNet or AS2 message, and then downstream via translation wrappers into the ERP system. This pattern exists in order to legally certify that an order has been received from the customer by the vendor, in this case HPE, and that the goods have been shipped to the customer in a legally binding, long-running transaction. There could be a significant period of time between receiving the order and shipping the goods. In this type of pattern, the components are specialized and equipped to provide status on the state of the transaction. So as you can see, within one small domain, we were able to identify a variety of architectural patterns that can be leveraged, evolved, enhanced, and reused repeatedly, giving development teams the ability to accelerate delivery of business value while reducing the overhead typically involved in creating a project from scratch. So what are the key takeaways from Module 3? As we saw in Module 1 and reviewed in greater detail here, within a single application as we define an app today, we can potentially identify many different architectural patterns. So conversely, multiple standardized architectural patterns can be assembled to produce a specific collection of functionality and user experiences. Just as we specify the architecture of a building, a few standard components like brick, wood, tile, electrical, and plumbing can be assembled in a variety of ways to come up with dramatically different structures. The bottom line, we don't need to reinvent the components each time we build a new structure. Pareto's principle teaches us that 20% of the causes are usually responsible for 80% of the outcomes, and architectural patterns are no exception. A relatively small set of architectural patterns, carefully chosen and assembled, can address most situations that a developer might encounter at HPE. The channels example that we examined as we reviewed the patterns exemplified this point. Obviously, there are always exceptions, but there will be the few rather than the many. We have tried to identify the most common and useful architectural patterns by examining in detail the 8 standard patterns listed here, and by reviewing examples from our channels domain in Module 1 within the context of the patterns listed here. The most basic pattern, the web services based on Addison, is extremely versatile and can serve not only as a web service, but as a proxy, an application middle-tier component, or even a self-contained web server. This pattern lends itself easily to reuse and will be found fulfilling roles throughout the various other listed architectural patterns. Simply add your own logic. So by carefully analyzing our designs in order to identify the required patterns, and then employing these patterns and their associated components when building our applications, we can save a great deal of time, enjoy the reliability of tested code, and thus focus our attention on adding or enhancing only what is missing, greatly accelerating time to value. We hope you've both enjoyed and learned from Module 3, where we have explored HPE's most common patterns in detail, and we have revisited our sample channels domain from Module 1, reviewing in greater detail the patterns found within that example, which is a real-world example. Arm yourselves with these patterns, and it will be far easier to design applications moving forward. We look forward to seeing you for future courses covering a variety of development topics using HPE's inner sourcing tools, intended to facilitate reuse and collaboration, and fully automate and accelerate the process of testing and deploying modern applications. For additional information, please visit DaVinci, HPE's developer forum.